Okay, fun stuff. Power electronics. So a little bit off topic, but actually really appropriately on topic because we still live in the real world. We still have to make all this stuff work. And all our mechanical systems, the way that they're operating is they use some sort of magnetic field, right, to either go electrical or mechanical back and forth. And so whether you do things with power electronics or just a standard AC system, it doesn't matter. It's not relevant, right? It's still going to have to use the concepts that we've developed this class, rotating magnetic fields, varying currents, et cetera, et cetera. But the world is moving more to a DC world. If you think about all the renewable energy devices that we have, right? We look at fuel cells, we look at solar cells, those output directly to DC. So if we could have DC systems or utilize DC systems more effectively, then we might be able to do something different. And then the other thing too is I've been working on a couple of projects, some offshore wind projects, massive projects, like 1,200 megawatt projects. And I just had a student in one of my other classes, a grad student, design a 1.5 gigawatt offshore wind farm off the coast of Maine. And what they use is they use DC to convey power from the substation. So there's a substation, literally it's a substation out in the ocean. And they're going to convey that power all to the mainland or to inland, or whatever you want to call it. And they're going to convey that with DC. So DC is going to be more and more important, even if you know, depending on your political leanings in terms of whether we're going to go with renewables or not. I mean, the future is going to be whatever is the most efficient and whatever is the most cost effective. At some point, you're going to start to see more hybrid vehicles, more EVs. It's just because the fuel economy is so much improved. And so if you can do more stuff with DC, you'll actually have some pretty significant advantages. So what do power electronics do? They're just valves, right? Some of them are on off, and some of them are control valves that have a basic position. All right. And so you're using some electronics to go ahead and either allow electrons to flow or to reject electrons, prevent them from flowing. And that's the simplest way to describe it. Obviously, it's a lot more complicated to do things, but it absolutely works really well. And how do you control stuff? You can control it with a computer. You can even control it with magnetics. It wasn't that long ago, and I actually had an opportunity. This is an older project when I was living in DC, that they used something called a magnetic amplifier. So back before we had power electronics, the way that we could control current flow through something is, remember the concept of saturation, right? If we're using a magnetic core to get current to flow through a transformer, for example, if we can saturate that magnetic core with some external energy, like a DC source, then you make it really hard for that AC energy to go through. So wasn't that long ago that they had these things called magnetic amplifiers, which would do exactly what power electronics do today. They would prevent a lot of energy from going from one side of the device to the other side. And so magnetic amplifiers were, you know, the precursors, if you will, to power electronics. You should take a look at them too, because it's old technology, but it's really cool in how they actually work. So I'm always impressed. What are the scope? Milliwatts, maybe even smaller than milliwatts. Think about your chargers for your cell phones, although some of those are 5 watts, but very, very small wattage, but you can get up to gigawatts. We talked about the HVDC systems, 1.5 gigawatts, major power. And 1.5 gigawatts, does that sound like a lot of power? To me, it does, but that's not that big of a system. The current DC connection from Canada into New England, which currently goes into Massachusetts, it's the only one, that is capable of 2.2 gigawatts. So another almost 50% increase from what these offshore wind turbines can do. So really the sky is the limit. What do you think would limit the size of any project like that? So I can go 5 megawatts, gigawatts, I can go 10 gigawatts. Why wouldn't I make a system that can go 10 gigawatts? You have some capital costs, right? So you have big upfront costs, but after that, it's not that much more expensive to go with higher power applications. Why not go with a 5 gigawatt line or 10 gigawatt line? Wouldn't physically be too big, but where it'd be too big is that what's that? No. It's more along the lines of if something happens to that system, like if there's a trip and the system trips offline, you've lost 10 gigawatts of power like that. In New England, at points in time in New England, it might be only 16 gigawatts of total load. You've lost more than half of your capacity. What do you think the grid's going to do when more than half disappears just like that? It's going to crash. Anybody paying attention to what's going on in Puerto Rico right now? They have island-wide blackouts because one generator goes offline and then the system can't handle a loss of that generation. And so before you know it, the whole island is black. And then as a result, it's much harder to bring the island back on. So the biggest limiting thing for a lot of these facilities is we just can't lose a system that's operating at that big of a value before our system becomes unstable for power system operation. So 2.2 gigawatts, when you think about New England being a peak load of about 28 gigawatts, that's almost 10% of its power going in at any point in time. That loss of power has to be tolerated by the system. So you can't just run the most efficiently, you've got to run by the most reliably, and then you start to move into efficiency. So it keeps going. Power electronics is going to grow and grow and grow. Devices not necessarily growing so much, but how to implement them, some of the circuit designs, it works really, really well. So what are the different devices we're going to look at? SCR, silicon controlled rectifier, not used all that much anymore. Triac, so those are really cool. A triac is a way of controlling AC. So power electronics love working with DC, right? Because you forward bias or reverse bias a junction, and then you get electron flow or you don't get electron flow. But if you have AC, right, at some point the cycle is going to go negative, and it's almost impossible to forward bias power electronic device because just the current flow itself wants to go in the opposite direction. But a triac is designed so that it can have current going in either direction. And we'll take a look at some of the device physics in a little bit. GTO, not the name of the car. Gate turn off thyristor. See a few of those. And IGBT, insulated gate bipolar transistor. We have power MOSFETs and those type of things, but the higher power applications, we kind of vary those a little bit. So here is the scale of power electronics, right? So 1/10 of a watt to about 10 watts, battery operated equipment, small power applications, maybe strobes, right? If you need a strobe or something like that, like the fire alarm systems that you see. Well, I guess we're not important enough in this room because they took it off the wall. But if you have fire, right, you have strobes and you have lights, those systems have to operate without any electricity by them. And so what you have is a battery that's constantly charged until it's needed, and then it discharges, and then it just pulses and goes from there. Then we move to 10 to 100 watts, which is kind of interesting. For satellite power systems, you only need 100 watts of power, right, to run a satellite. So you're communicating a lot of data back and forth, but you don't need significant amount of power for that. An offline flyback supply is just a flyback is a flyback diode, so the voltage gets too high and it reverses polarity and you can get some problems. Yes, sir?
Kind of a silly question. By satellite power systems, are you talking about powering a satellite or one node?
No, it's powering a satellite. Yeah, because a satellite, once it gets up in the air, right, you got to run it off the power. So you use a PV array up there with a battery. Remote power around here, yeah, no, that would be. Yeah, but we're talking about satellite communications because a satellite here could be, I have a satellite office with 500 employees, right? So that scale of 100 watts, right, it would be a lot more, yep. Yeah, that one would be too broad. We're talking more about the ones in the sky, that thing. 1 kilowatts, amazingly enough, if you have a tower, does anybody know what I say for a tower PC? You do? Oh, wow, okay, I didn't know. You have, you still can buy tower PCs?
Oh, you can certainly buy them.
Okay, I just thought that everybody had laptops or tablets. I didn't know people had made tablets, unless you're a serious gamer. What's that?
Well,
yeah, you gotta carry it around. Sure, but I think you know, unless you're really a high-end gamer, most of the time, the performance in a laptop is plenty, isn't it? Or not? I don't know.
You try to, you get better thermal properties with the time.
Sure.
Yeah, and if you try to drive like a higher end monitor, like a 4K monitor, you can't do that.
Oh, you can't? Oh,
You can, but you can't lower like frame rate, but it's gonna be cheaper. Well, there's, you know, like the discrete graphics card.
Yeah.
Laptop, and the equivalent, if you could have an NVIDIA, say a 4060 on a laptop, it's not the same as a 4060 on a desktop.
oh, okay.
And it's also the thermal performance too.
Right, because you have thermal performance, let me back up a little bit. Thermal performance on a laptop is you have to really be optimizing thermal performance, right? Because you don't have much heat sink area to remove it. With a tower, you can have a giant fan moving a lot of, you can even go liquid cooled systems. So those don't have to be as efficient, right? I'm assuming, I don't know, but maybe they can do more flops per second or whatever the standard, you know,
Well, ideally, you're, you know, adequately cooling system. So
Right.
you can push it to the point.
right, you can get more performance out of it. So maybe like super high end, and I don't know, I don't, again, I'm not a super, but I don't know when you would need that type of power. Even serious gamers, I thought everything was done online.
No, your average gamer uses probably a tower, but if you get a tower.
Oh, so it's not because of the power needs? Okay.
No, it is mostly for power needs, and it's also for the upgradability. Like you can't, it's not, you can't really upgrade this, like you can.
Right.
That's about it, like you can actually make this one higher. That's one for CPU.
Motherboard, all that stuff you need to, yeah. Well, the reason why I say that is because it's not that uncommon to get a tower with 1,000 watt power supply. I remember they used to buy them 1,200 watts, 1,400 watts. This power supply right here for my laptop is 65 watts, and that can charge the battery while it's cranking along. So 1,000 watts, right? Getting to be a lot of power, and that's all DC, right? So it chops up the waveform and gives us DC because the computers work on binary numbers, right? 1 or 0. You couldn't necessarily work on AC with computers.
Computers are mostly, they only have like a 12 volt, 5 volt, maybe a 3.3 volt signal.
Yeah.
Coming out of the power supply.
Yep, which is kind of a drag now because you're pushing a lot of power, right? You need a lot of, you need some
Yeah.
pretty sizable bus if you're running it at 5 volts or something like that. Where if you're running it at 50, you know, you can cut the current by, I mean, the current size by quite a bit. So, but then you have to space things out, the boards. Yeah.
That's actually one of the big issues right now is NVIDIA released the new graphics card that draws 600 watts. Over a 12, yeah, which over a 12 volt connector, which is just like, I don't even know how much.
50 amps.
Yeah, exactly. It's 50 amps over just like a.
And that's just, that's output power. I can't imagine what it'd be for input, but I don't know if that's input or output.
That's input power, yeah.
Yeah.
But the problem is that they're it's 6 power and 6 ground. And the problem is that they're not doing current regulation on them. So some of them could be higher than whatever 50 divided by 12 or 50 divided by 6.
Yeah.
Some of them are going up to like 12 amps over the tiny little wire. I think it's just 12 wires and panel from the power supply for that way. Yeah, exactly. Because at that point, you can't even power it from the motherboard. You need
Yeah.
an additional power supply that runs
Directly to it. Well, and that's the problem too, right? Which is if you keep doing this stuff, at some point you just got to switch to bigger voltages. It's not hard, right? We can, but we're just stuck in these old ways. Automotive systems, 12 volt auxiliary power supply is nuts. When I've got a hybrid battery that has a 400 volt system, but oh no, I can't go 12. I can't see 12. Why not go to 36? You got a lot of margin there, and you're still below 50 volts, which is what the National Electric Code prescribes as a be careful voltage. So.
Is there an issue with doing that? Like is there anything that's really changing the system to go from 12 to 36 volts? Like,
You
change a lot of stuff.
Well, you'd have to change all your devices that are designed to operate at 12 volts, which is how many trillions of auto parts have been made to operate at 12 volts.
So it's expensive.
Well, so, and again, it used to be, if you look at old Mercedes, I think they used to run 48 volts, but some reason people settled on 12 volts a long time ago. But that's when you had, you know, 30 amps of max current draw on a car, right? I mean, you had a radio, and you look at some of the old heating systems, right, where they would just open up a flap. You had the windshield wipers and maybe a radio. That was it. Now, I mean, every car has got, I don't know if you can buy, and I think we talked about in this class, I don't know if you can buy a car without power windows. So you just have such demands. Yeah, the hand crank windows. my last car, I had a car I sold, it was a 2001, I had hand crank windows. And now, yeah, I'm sure you can get them, but
It's
they're,
like super, yeah.
yeah, they're pretty far and few between.
No, I think it's like ridiculous. Yeah.
Right, so the idea is let's transition away from 12 volts and go to 36 volts, because all those fuse, I mean, if you look at the fuses on a car, it's just nuts. I mean, the fuse panels have gotten so incredibly complex, whereas you could just do everything at 36 volts and still be far away. A good one, an example is tractor trailers. They run 24 volt DC systems because they have major loads, like they have microwaves and they have, you know, cooking things in the back of these things, so they have a big demand, and they run 24 volts. But how do you get 24 volts? You take two batteries, you put them in parallel in series with each other. That's basically what a truck driver does when they need the capacity. So yeah, we should go away from that. Hot tub, they use power electronics because they have an electric resistance heater. And so you just switch off the resistance heating. So you can get, you know, a certain temperature and you can maintain it, or you can jack it on or off. But most of them, I think, use a simple power electronics to make that work. How about an EV? I only put 10 to 100 kilowatts. But if you're really in the super duper high performance stuff, you can actually look at some of the ones that are pulling more than that for short bursts of time. I think Lucid, as a company, makes a car and you can put it in a special mode that basically, like, you only get 500 operations because it degrades the warranty on the battery so much. So it actually locks you out. It's like a launch control type thing. If you want to move to an EV bus, 100 kilowatts to 1 megawatt. Then we go on to SEMS, which are superconducting magnetic energy storage. So back before batteries, you have a question, Noah?
I know they have some electric buses,
Yep.
but they are not battery. They run.
Well, so it depends, right? So if you look at the traditional infrastructure, yeah, you would go ahead and use overhead wires. But if you could have a battery system, if it was economical, and it would last a lot of miles, wouldn't it be easier to just do a battery instead of running all those live wires all through the town, and people have to make sure they're connected and they limit your routes and all that stuff? Those usually aren't necessarily buses. Those are more like a light rail system with a heavy duty buses, but they have a very prescribed pass. Where city buses, you know, go on all these streets. So they have some of the ones in Europe, they use hydrogen for powering them. But again, the problem with hydrogen is that you just don't have the energy density. And so you need to pump your tanks up to crazy high levels. So if you could run it on electricity, it'd be great. There were school buses in Maine that were electric, but I guess they didn't work so well.
Did that keep working made for how much further?
No, it works fine as long as you have the capacity. The problem with buses or with any batteries, what happens in the winter? It's too cold, and then the battery, like my battery in the summertime, I can get 12 miles of electric range if the temperature is good. But right this morning, if I can get 8.5, it makes me happy. And in the dead cold, 7.9, 7.8, so almost half the capacity disappears, because there's two reasons why battery capacity disappears. The chemistry changes, but also batteries don't like being cold. And so it actually uses some of the energy in the battery to heat it up faster. So it actually will make heat to warm the battery up.
You set your location of the temperature.
Yep.
It will precondition the battery.
Yep. It's ready to charge. Yeah, that's exactly right. So they're pretty good about it, but it does cause some problems. Superconducting magnetic energy storage devices, again, before batteries, all we would do is take a flywheel, rotate it at 80,000 RPM, and have it just spin, and that was our energy. And so if you needed a short-term power supply that was pretty energy dense, you would do it with SEMS. You don't see them much anymore, but they still are around. How about the next one? These are the next generation aircraft carriers, right? Magnetic aircraft. So launching a plane off of a, what's that? Yeah, exactly. Yeah. You can use a lot of power. You can fire it much more efficient, much higher speeds, much more available torque than the steam systems. Works super duper well. And also, how about in New York City? How do the trains get around? Though they have to use electricity, because you're not going to run diesel locomotives under the tunnels, right? Everybody would be dead on the trains. And so they'll use DC motors to provide power, but those would be actually connected with wires to make the connection. And then a power plant, usually 100 megawatt to 100 gigawatt. As I mentioned, just down the road at Maine Independence Station, they have a 50 megawatt power electronic device to be able to start that synchronous motor, the synchronous generator up as a synchronous motor. And then greater than a gigawatt is the Sandy Pond substation. Let's take a drive, if you will, to Ayers, Massachusetts and Sandy Pond. Here it is. Can you tell which is the DC station and which one's the AC station? Oop. Yep, so you know where the transmission lines are coming in, but I've got, this is an admin building. Over here, you can see some electrical stuff. And over here, you can see some electrical stuff. So is the DC substation here or here? Or can you tell? You want me to zoom into the top one or the bottom one? Okay. I can do another one. Let me zoom in. We'll do the top one over here. Is that zoomed in enough? Okay. Let's go to the bottom. This is AC. And this is DC. How can you tell? Bus bars are instead of 3 over here. What about over here? Do I have 3? I'd have 3 over here, right? Been to a lot of AC substations, have you? Well, let's take a look. So this is AC, but I've got 3 phase over lines over here, so that's not DC. How about this other side? That's AC. See the 3 ones? How about, there was one more coming up here. How about over here? That one I can't really see all that well, right? So let's drop our, where's the street view guy? Let's look up. I got 3 phase, there's DC right here. So the one to the left is the DC line. Kind of hard to see, that's not a great picture, but it only has 2 phases there. So, yeah. Plus and a minus, right? I call it phases, maybe that's the wrong term. Oops. It would be poles typically. I don't know why this is not, like, this thing will not go, there we go. But yeah, this is the DC substation, and this has the capability of right up here, 2.2 gigawatts, which would make it the largest generating facility. I think it's even larger than Millstone. I mean, yeah, Millstone, which has 2 units. I think Millstone is around 2,000, maybe 2,100. So that's here. Why do we use DC? In this case, we do it because Hydro-Quebec does not want to be locked into the frequency for the United States. So we have to run DC so we can run asynchronously to them. The other advantage is because you actually can get smaller lines, because remember we talked about the skin effect with AC resistance gets higher than DC. So you actually have more power loss in an AC line than you do in a DC line. Those changing magnetic fields will concentrate the power in the center of the line and will cause you some problems. But very, very, very expensive because those DC converter stations, super expensive.
So what can you look at there that's like different than things you find in them?
Probably the biggest thing we could see is this building right here. No, not something that tall. I mean, it's hard to tell, but this is a single story and this is a dual story right here. This is all the electronics. And you used to be able to get tours in here. It's like a giant fly trap when you walk through it. You're walking in the center of the 2 poles and you see all these dead mosquitoes and flies because it's basically a big bug zapper. They go anywhere near there. And the thing about this one is this is plus minus 450 kV. So it goes plus 450 relative to ground and minus 450 relative to ground. So the actual potential difference between those 2 incoming phases or poles is 900 kV. It's almost 1,000,000 volts. But you can although they don't allow it in the United States, you can operate one pole or the other. You could go 450 to ground and it would still provide electricity. And once you get to Canada, they don't actually run that center DC back. They actually stop it. They just run the 450 there. But in the US, they require you to do that. But this was built in the 80s, mid 80s, and they've upgraded all the stuff since then. But yeah, huge benefit because up in Montreal or north of Montreal, they have all this hydro available. They have 35 gigawatt of hydro. Was basically free for them, and they don't have the needs for it, so they just ship it to the US. So one of the things you think about tariffs, right? When they talk about the costs, I mean, energy costs aren't excluded. So there'd be pretty big hits. New England, they talk about what's happening in Ontario and going across into Michigan. We would have the same problems here. 10% of our supply is from Hydro-Quebec. We'd have the same issues. New York also has a DC line that comes in. So there'd be some pretty expensive changes for us. If you want to look at some of the power electronics, here is a figure. And essentially what you see is these are these valves with some transformers. That's kind of the on-off switching of it. That's basically what you can do with power electronics, is switch things on and off. All this other stuff, if you will, these are inductors, they're filters. Their whole purpose is to filter out all the high frequency stuff. So it doesn't go back into the line and it doesn't end up on the DC line. So it doesn't go back into the AC system or the DC system. It all gets shunted to ground, as you can see. Okay. That's the biggest problem with power electronics, is it's just on, off, on, off. And that can cause a lot of problems in the physical world, because in the physical world, we don't like going from 0 to 1 instantaneously. We like it to smooth out. And so those systems respond quite harshly to those instantaneous changes by generating lots and lots of harmonics. Okay. On which one?
The small area. In the back of the ear.
Oh, here? My best guess would be 345 kV. Well, we don't really have, oops. It's hard to tell, but I can tell you, if we look over here, we can zoom in. These two poles right here, remember, that's 900,000 volts between these two.
Yeah.
So over here, it's hard to tell, but it's an H frame, and you can see there's one pole, there's two poles, one phase, two phase, and it's dual conductor. And most of the time, at least in the Northeast, the only time you see more, when you see what I call bundle conductors, when you said dual conductors, is when you're 345 kV and above. That's typically what you'd see.
I agree with you there. I was thinking with the yard. You think that's pretty way down?
No, what comes in the yard in this one?
The other.
Oh, over here, it's probably a mix of 138 and then some sub transmission stuff, if I had to guess. I don't think any 130, I don't think 345 would be coming out of there, no. Yeah, but some of these line might just bypass it completely. This is most likely, small potato stuff, because you can see there's, yeah, and it's an old substation too. You can see those overbuild where they have those, it's hard to see, but when you see steel structures like that sort of over, you don't see a lot of those anymore. A lot of that stuff is done either, you have a dead end tower walking in and then you'll go underground and do it. You just have more stuff underground. So having the steel that's up above is not the most current way that you see things designed.
What's the purpose of that?
Probably because they come in and they have switches that go down. So it's just a way of getting into.
Literally a way of
You can see here this three-phase line. This is a dead end structure here, and it drops down in between. It's very complex to have a setup like this, because maintenance on this, look how hard would it be? Hey guys, go fix this breaker right here in the middle. It's probably an independent breaker, so they can change out each phase as necessary. But would you want to be driving a truck through here and, having a hoist and a crane in the middle? I wouldn't. Yeah, this is not an easy one for maintenance. And that's the other thing too to think about, right? When you're working at high voltage systems, 115 kV, 345, you're trying to maintain these things. You have to maintain a lot of the systems when they are energized. You can't shut down a substation like this for any real period of time. Why? Because all these customers might be losing power, or you have to reconfigure the power there. And that's a lot of work to shut a substation down. That makes a lot of people unhappy, and prices will go sky high. So yeah, that's Sandy Pond. And like I said, we used to get tours of that place, but because of CEII, because of CEII, we're not allowed to go in anymore. All right, so it's super interdisciplinary because power electronics can drive anything, right? We can use it to roll up and down our windows. We can use it to operate an antenna, or we can use it to act as a VFD or an ASD to go ahead and get it to work. So it's the way that a computer can interface with an electrical motor without just turning it on and off. You can adjust the speed. You can do all kinds of different things pretty easily. So it's the center of a lot of things. And a lot of this stuff, right? Solid state physics, that's where we go device characteristics. If you remember from NPN or PNP, you know, if we look at our old BJTs, there's a tremendous amount of device stuff there. One of the challenges with power electronics is now you have nonlinear systems. So your simulation gets to be much more complex when you're simulating operation with power electronics than if you didn't have to do that. So really makes it much more difficult to analyze those systems. Excuse me. So what are some applications? Kind of crazy, but heating and lighting, right? If you want things to not be on off, if you want them to be in degrees, you can use power electronic for heating and lighting control. And you can go down to Home Depot and for $7 buy one of those sliding switches that you can adjust the light output. And it doesn't have to be incandescent, it can be any different style. That's all done very cheaply with power electronics. Induction heating. So you're on your cooktop and you're cooking away, right? I want more or I want less. The way that mine works, and I have a cheaper stove, is it's on for 5 seconds and then it's off. But the induction ones, they don't do that. They don't go on off. They have more current in or less current in. So they have a fancier device that turns that off. Lamp ballasts. You don't see fluorescent as much anymore. Most stuff. Excuse me. Has switched to DC, but you can still buy fluorescent. They're still pretty reliable and pretty efficient. Power transmission, we've just gone through that. Automotive, perfect application because we have a DC system. There is no AC in an automotive system unless you plug in, you know, like they have an inverter now because most cars, I should say most cars, some cars come with an AC outlet, right? You've seen the 3-prong outlet on some of the cars. That's not that uncommon anymore. So they put an inverter just for that specific one. But everything else in the car operates on DC. Now you can say, hey, wait a minute, Paul, you told us that you need that rotating magnetic field, which you have to produce from an alternating current. Well, with DC motors, we can get an alternating current just by swapping poles around. So it's easy enough to do. Ignition, go ahead.
Okay. Cigarette lighter style, what that comes with?
Well, this is even before my time, but people like to smoke, right? So
Is it exactly the same thing, like when I stuck a cigarette in there, but it?
no. So the way a cigarette lighter used to work in a car, and I don't even know if they make them anymore, but you had that part, and then you had like another, I don't know, plunger that you'd push on it, and what would do is it would have current flowing into the cigarette lighter, and it was just a little resistive electrical heating element, and it would heat up really quick, but it would get hot enough so that you could light up a cigarette, I guess.
Somehow we standardize the.
Yeah. It was round because I guess the cigarette was round, or maybe it had to be big enough for a cigar. I don't know. But cars used to have ashtrays. I don't even know if ashtrays exist in cars anymore. I'm not sure if any of my cars have ashtrays. Maybe they do, maybe they don't. But
I did see nicotine patches related to actively.
no, well, maybe she need the extra hit. So that works. Whatever works, but yeah, nowadays I don't think you do because everybody vapes now anyway, right? So that's the new cool thing. So I guess. Electronic ignition, power electronics. Why do you need electronic ignition? Because you need 2000 volts. So you can use buck boost converters, right, to generate whatever voltage you want pretty cheaply. Whereas back in the old days, anybody know how they used to get, well, they had a spark plug, but how would that actually ignite it? You used to have a distributor cap and it would pulse an electrical signal every once in a while to the spark plugs. So now I don't think they've had distributor caps for almost 50 years, but before electronic fuel injection, electronic ignition, that was the standard. You had an old distributor cap with a rotor button. It was quite a process. We talked about adjustable speed or variable frequency drives, battery chargers, hopefully pretty obvious. You're going to convert the AC to DC, but you have to do it with intelligence, because if you have a lead acid battery, you charge that battery, you can't just charge it, stick it at whatever voltage you go. You sometimes have to equalize, sometimes you have to float, just because it prolongs the life of the battery. And then we might go with a nickel metal halide battery or lithium ion battery. So there are different types. I think for mostly in the utility industry, we still like lead acid because it's easy to check the quality of the lead acid battery. Anybody know how you check the quality of a lead acid battery? You don't measure the voltage. Taste it. Be my guest. Sort of on the same way, though. You take a sample of the lead acid and you run it through a test and you look at the specific gravity or specific, I don't know what it is, but you actually would take a sample out of it, and then you can tell the quality of the battery and how many years it has left just by looking at whatever that fluid is. And so some of the procedures that people do, if it's really a critical battery, is they periodically have to go and measure the lead. I think they do that for utilities still.
You just completely discharge and recharge it.
No, you try not to discharge or completely recharge, because that degrades the life of the battery. So every once in a while you do, like, depending how severe it is, if I have to have a battery that can put out 400 amps for 8 hours and it's like mission critical, yeah, I would want to test every year or 5 years, whatever it is, to make sure that battery can do it. But cycling a battery like that, actually, drawing it all the way down is really bad for a battery. So you have they're special batteries so they can handle that a lot more. But yeah, you try to keep your batteries fully charged as long as possible. They last longer.
So if you drop it down to about half.
But the problem with half is it's not a one-to-one comparison. Half of a charge is not necessarily half the voltage. It has to do with so much more. So generally, yeah, they just do a surveillance test. And batteries are, they're not moving parts. So as long as the acid's good shape and you don't see a broken terminal, it's a pretty reliable device. It should last a long time. Alternators, right? We have alternators in our car, unless you have a hybrid car, and alternators basically have power electronics, and they convert that three-phase AC into DC. Energy storage, right? We talk about battery storage stuff all the time. EVs are the big ones. And then for anything solar, wind, or fuel cells, we need some sort of power electronics to make those work. So sorry, I still have a cold. I think this is a new one. So what does power electronics do? It's DC to AC, DC to DC, or AC to AC. That's essentially what it does. All it's doing. It might change frequencies, but the only way you can change frequency with AC to AC is you got to go to DC first. So we're kind of not necessarily showing that step, but that's what our power electronics do. Here's PV. Output of a PV array is DC. And the solar controller on a PV array is also what's called a maximum power point tracker, because solar cells are perfectly happy to put out maximum current with no voltage, like in the case of a short circuit. So the solar controller, the maximum power point tracker, is actually forcing the voltage across the solar array to be at its maximum, balanced with the current that's going out. And so it's always tweaking it to force it to provide power. That runs to a DC bus, and then you can or cannot have a battery bank. So some of the renewable energy projects you see, they have a solar array that's bigger than what the transformer is rated for to export to the grid. And so they have a battery system in the back. Why do you think they would have battery system in addition to a solar array? Why won't you just take all the power and dump it onto the grid? Why include the battery bank? Exactly. Yeah. Yeah, you've got capacity at night. When the sun goes down, your battery bank is there to help support the grid. So works really well. If you have that battery bank, though, your inverter has to be a little bit fancier, which means you need to have bi-directional capability. Power can go in either direction because you may want to charge that battery up. There may be times that you need to charge the battery. If you're only selling power to the grid, probably not, but there may be applications when you do. The other thing too is sometimes you might want to run testing. So you may want to energize that DC bus from the utility, not from the solar system, from the solar array. Solar, yeah. Then you have an AC bus where you can add on some AC loads, and putting on power systems AC can be more challenging. So that makes some challenges. But if this is a critical power system where you had to have backup, go ahead and put a recip on it, right? Reciprocating engine. Most of the time you like to use diesel because it's more fuel efficient. You don't like to run gasoline. Diesel is also better because it has a longer stable life. So you can put diesel in the bottom of a car, and 2 years later, it's still diesel. You know, as long as the temperature's been maintained, it still operates perfectly fine as diesel. What's a converter? Excuse me. Converter just converts from AC to DC. Most of the time, when we use terminology, we have a battery charger to mean we're going from AC to DC, and we use an inverter to go from DC to AC. That's the only difference in terminology. We can use a switch mode power supply, which is what most of our computers use for power supplies, is switch mode, but it's total trash. It's called a Class D power amplifier. And what it does is it chops up the AC waveform by just turning it on and off really quickly, and it makes a very efficient power supply. But a very crappy one, it creates tons and tons of harmonics. So if you're really into audio applications, it used to be that you'd want a Class A amplifier. You had more money and than you knew what to do with. But Class AB was like the next step, and you had a little bit of choppiness. Class D was the worst in terms of quality, and probably still is. But why do you care? You know, how many people here are audiophiles and only want the best speakers and all that stuff? First off, you wouldn't be putting it in your car. And secondly, it's not going to be that good quality, going to get road noise and all that stuff. So yeah, you don't often see it. Have a bunch of different rectifier designs in here so we can control them or uncontrol them. Most of the rectifiers we use are uncontrolled, right? We talked about bridge rectifiers, which are just dumb devices that conduct in the forward direction as necessary. You can have semi-controlled or fully controlled. And if you're doing fully controlled, you're trying to chop the voltage up to get whatever characteristic you want. We don't do that a lot here. We just rely on the DC, and then we use a voltage regulator, right? We'll take a voltage regulator and it'll reduce our voltage to whatever values we need. Those work really efficiently, well, not efficiently. They work effectively, but not very efficiently. So I'd be careful about that. And then you can go single phase or 3-phase. You can get all kinds of different options and configurations there. Then we can go from DC to AC. Emergency lighting, right? You got to have a battery pack. So all those emergency egress lights to get out of the building, or exit sign lights, those are all built in with their own batteries, and they're permanently sealed. They work really well. Variable speed drives, we talked about that, right? You're going from a variable frequency, so you're going from 60 hertz to a bunch of different frequencies. The only way that you can do that is from AC to DC, and then back to AC. A UPS is another way to say a battery, essentially. So I don't think you see them all that common anymore, but there was a company, Aztec. They used to make power supplies for laptops. You would see them on people's desks. They had this little Aztec, I think it was Aztec was the brand name, or maybe it was a Copian, I can't remember, but you would plug it into the wall, and then you would plug your computer into this power supply, and it had a 1-hour battery. So if power was lost at your house, you could keep the party going. Yes, sir. No, they don't have them in control houses. No, most of the time, if you're in a control house, everything in that control house that's important is fed from the battery bank, which is fed from an inverter. So in most control, the ones that are critical, you run them directly off DC. But if you can't do it, like if you have a computer, what you do is you run one DC circuit over, and then you run that through an inverter, and then you have like the orange or the red outlets to indicate this is on the UPS. So you can't plug in a toaster oven. You can't just keep degrading it. So critical ones like that, you'll run it off the AC. If it's a small one, like if you don't really have any critical loads, then you just say, okay, well, we'll have the lighting, we'll have its own battery packs and stuff like that, go from there. But yeah, you got a big battery, you might as well use it for that.
maybe not necessarily a control house, but
Well, that's different, right? So in a control house, the RTU and all that stuff would be on the battery system. Right? It would have a DC input. It would not run, it would not be plugged in to an AC system. And I've designed power supplies where I had 120-volt, we call them vital buses. And so we would have the battery charge, we have dual battery chargers feeding a battery. And then on the output of the battery would go to a DC panel board. And one of the loads would actually go to an inverter system, and that would be a UPS that would run all the critical AC loads that the plant had. So yeah, that's pretty common for power plant. And then a frequency converter, another way to say adjustable speed or variable speed drive. Some of the things we can do for DC, and again, we're not going to get too much in this, but switch mode power supply, again, just switching something on and off and step it down really easy. You can do a chopper, which basically is charging up an inductor and forcing it to go to a higher voltage. Flyback converter, we don't see those that often, but again, it's using that inductive kick that we would go. And then a resonant converter is just using the concept of resonant to be able to charge and discharge. There's a lot of description on that. The only thing I really want to focus on is the triac. So the triac is the AC converter. You can get a triac to switch on a 120-volt signal. Okay, 120-volt AC. It's one of the very few devices that will actually work with AC. How about this? Why did I put this up here? Because everybody loves their car radio, right? We had a student here a few years ago that he was really into performance or competition car stereo stuff. But his car stereo stuff was like how loud it could get. Like they would have, he was telling us like he had a special car that he didn't have windows in the car because they would break. It was all plexiglass. So he had to change out all the windows to plexiglass. And the idea was you would turn it up with these big speakers and you would see people sitting there like their hair would be moving around, pulsing to the beat and the bass. So he was using, 5,000 watt. I guess all the real super power amplifiers were made out of South Korea, I think. But yeah, he did competition stuff in Winslow, Maine. I think his business is still there. But how did he do it? Well, first off, he had a pretty fancy battery, but more importantly, with that bass hit, you need to store some energy. And so what he would do is he just had 10 farad, 50 farad, 100 farad capacitors that would help boost the battery. But the amplifier in here is just a Class D amplifier. It can run whatever application, whatever power you need, but it runs it efficiently. It's just not very good audio quality, especially for the sub amplifier, right? So when you're getting that low frequency stuff, all you need is that thunder, pound, pound. So you're not really looking for perfect representation. You're just looking for the thunderous bass. People want the volume, they want the pounding. They don't really care that it sounds exactly like the music was made. So you can see something simple like this. But yeah, pretty simple design, right? We have 4 speakers and a sub. This is a pretty cheesy system compared to today. Most of you probably in your cars probably have like 18 speakers or something crazy like that. I mean, you get tweeters up here high, and then you get some in the lower door in the driver's side and some in the passenger side. Then you might have a sub in the back. I mean, they're getting to be a lot fancier car speaker setups. But I don't know about you, but I spend most of my time with my headphones in and just kind of listen to a podcast in peace and quiet. But yeah, power electronics just in your car stereo system. Interesting. So this talks about the limitation of our 12-volt system. So if we talk about an amplifier today, you can deliver at least 40 watts. 40 watts is probably a minimum that what you want to provide. But most of our speakers, I believe, in car stereos are 8-ohm speakers. Everybody know, like there's a 4-ohm, 2-ohm, 4-ohm, 6-ohm, and 8-ohm speaker designs. They have the different ones. But the standard in car stereo is 8-ohm. Interestingly enough, is if you have a 12-volt supply and you want to apply that to an 8-ohm speaker, V squared over R means what? 144 divided by 8. So you can only get about 18 watts at 12 volts. So what does the car stereo do? It runs at the amplifier, it runs at a lot higher voltage than 12 volts. So even in your car, even though we say it's 12 volts, some of the individual systems might actually run at a much higher voltage as in your car stereo, right? Because you're pushing, 40 watts is not a lot, but that's the standard. I think if you go buy a car amplifier today, 500 watts is not that uncommon for what you would find. So, and you can do the same thing at home, because at home, you're not limited to that 12 volts, right? You get whatever you're coming out of your speakers or the speaker wires, you can run that up as high a voltage as you want. I don't know how high they would get, but I'd imagine if you're pushing more than 100 watts on a home speaker system, that's pretty loud. So, do the math and figure that out. But I would imagine that that would be more than what most stereo systems can handle. How about hybrid electric vehicles? Lots and lots of power electronics on there, because a hybrid vehicle doesn't do anything for us unless you can store that energy, right? That's the whole purpose. We talked about in this class, we talked about regenerative braking. And regenerative braking is when you hit the brakes and instead of using the actual, the friction that you get from the brake pads coming in contact with either the discs or the rotors and generating heat, you take that energy that's stored in the vehicle, right? Because you've got some inertia and you slow it down, you convert that energy, instead of heat, you convert it back into the battery. So, work super duper well. So well that, let's see. Anybody into Lucid? Lucid, I think, still makes the king of the hill in terms of the distance, but you got to go pretty high, right? So this here is, and again, it only tells you $69,000, but from, right? So $70,000, you can get a pretty nice looking car. That's the Lucid Air Pure. What's that? Well, but if you want to get the super fancy one, you need the Lucid Air Grand Touring. Has all those bells and whistles, but take a look at the range. $480 miles. A lot of people don't want EVs because of range anxiety, right? That's one big reason. But 480 miles, that's 60 miles an hour, right? You're doing 8 hours of driving. What's that? I don't know, 819 horsepower. That impresses me a little bit. But you can see, I mean, now again, it probably gets you 480 miles, but that's only when you're doing like barely touching the throttle and you're coasting a lot, you're being really conservative. But 480 miles, even if it was half that, 240, it probably looks good for most of us. The Tesla Roadster? Is it out already?
No.
Oh, okay.
But, can't really believe. No, of course you can't believe that. It's 620 miles a 100, right?
Well, but it says here, it says EPA estimated range. So this is not something that they, just dream up and put this crazy number on. This is here. And again, you can buy this right now. This says available cars, right? So I'm not saying there's anything within, a stone's throw from Orono, Maine, but you can buy a Lucid. And I do have to admit, a pretty sharp looking car, right? I mean, I don't know if you all are into sedans, but looks pretty cool. And this is not a car that's made for miserly, like my Prius is made for basic bare bones commuting. This is not. Then an EV, I put this up there because this is a pretty good job if you want to learn about how an EV works and all that stuff. It's a little dated in some of the stuff, but it does a pretty good job of giving you some of the information of how the powertrain works, because it is sort of more complicated, because when you have a gasoline engine, there are different concepts. Some people want to drive the wheels directly with the gasoline engine as well as the electric motors. Other people want to drive them directly with the electric motors. It just depends on what the application is. So you just have to be careful that, the different designs are doing things. I think Subaru is coming up with a slightly improved way of doing things. But Toyota has been doing it for many, many years. They've had a hybrid probably now for 20 years. So yes, we can do all the different ones, but it's got to be reliable too, right? It's got to be able to drive for 15 years for 200,000 miles or whatever to go ahead and make it worthwhile. But in either case, right? Your electric motor may not be separate. Usually it would be the same, right? If you have an electric motor, you want your generator, unless everything off the engine is run off of electricity. At that point, you could have a generator. And so in that case, what you do is you run your engine at as close to optimal speed, meaning if it runs the most efficient at 2000 RPM, that's where it's running. And then it's always charging a battery, and then that battery drives the motors. So again, you can take a look at all the different things. Like I said, the car, it's a plug-in, so it's a partial electric vehicle. Like I said, I can get 11 miles out of it, but sometimes is a bit of a drag because it's not the quietest, most comfortable car, but it's pretty efficient. So all kinds of different things in hybrid and electric vehicles. But the whole thing is, all this works because of power electronics. We have those motors, and they can be synchronous motors, they can be induction motors, but in any event, if we're trying to control speed, so we want to go 25 miles an hour, not 65 miles an hour, we have to have the capability to either increase frequency, decrease frequency, increase voltage, reduce voltage, all those different things. Now, one of the things that are making EVs a problem is it has nothing to do with the powertrain. Because if I have, the Lucid or the Tesla and I want to do 200 miles an hour, the electric motors can do that, no problem. Well, I shouldn't say no problem, but they can do that. They can put out enough torque, probably indefinitely. The issue becomes when you're pulling that much energy out of the batteries, you degrade the life of the batteries. So the biggest limitation on EV penetration today is the batteries. And if you think about battery, we've had lead acid batteries for many, many years. Battery technology has not jumped leaps and bounds over the past 50 to 100 years. There was no reason for it. Now you're starting to see where it's becoming a bigger and bigger issue, but it's still the same basic technology. We're just trying to do things easier. So maybe there should be an addition to this class, which is, battery technology, but that's all chemistry. So I wouldn't hazard a guess as to how to do that. I'll let you out a little bit early. I'll keep going for a few more minutes, but this is just bonus gravy material. So a diode, simple enough, right? Here's the sketch or the figure, the schematic figure on the left. And if you ever get confused, see where the arrow is? For me, I see this arrow. Oop, why don't you want to? I'll draw extended. That's an arrow pointing to the right. That is where the current will go. This, to me, it's a wall. Yeah, it blocks. So, yep. And no. Current goes from left to right, but not right to left. Unless, and again, remember, you have a junction here, right? And you can see that with the figure over here. This diode is perfectly happy to conduct in the forward direction. You can see as I increase the voltage here, I start to ramp up until I get to basically a vertical line, which means that I can't increase the voltage any higher than that, because at that point, the maximum amount of electrons are going through. I'm not going to get any more of a voltage drop across that. So let the current roll through as much as it wants. In the reverse region or the breakdown region, it is putting out no current. It's blocking all that current because the positives and the negatives are separated from each other and they're getting worse and worse. Until such time, if the voltage across there is so high that it basically will just arc across the semiconductor devices in your diode. Yep. And then it'll conduct. And at that point, most diodes are fried. Zener diodes are not. But regular diodes, if you operate them in the reverse direction so much that they start to conduct, that diode is probably toast. Okay. And you can see that here when you call it this avalanche breakdown. That's when, at that point, the diode started conducting, and see you later. Go ahead. So here's a Zener. And again, a Zener is designed to actually operate. So take a Zener diode and operate in the forward bias direction. It works just like a regular diode. In the reverse bias direction, that's the only time you'd use a Zener. Otherwise, why not just get a standard diode? But in this direction, if it's plus to minus here, it blocks until such time that there's enough voltage for it to conduct in the reverse direction. And it's not a perfect forward biasing one. It does pretty well, but it's not perfect. And so at that point, it's going to allow current through. And a Zener diode is usually really good for providing a reference point. So if you operate a Zener diode in the reverse bias direction, you can set it for 10 volts, 12 volts, and it does a pretty good job of maintaining 10 or 12 volts. If the voltage drops below that, there's nothing it can do. But if it's above that voltage, it'll try to conduct more current and get a bigger voltage drop across the system. So Zener diodes are really good for references. I want to get 10 volts at this point, so I'll stick a Zener in there and it'll work. They're simple devices. You can get fancier voltage control devices, but these things are 3 cents a piece. No.
What do you mean that?
Say that again?
What do you mean when you say set for that?
You basically have purchased a Zener. Right, you set it for a specific, so that way the manufacturer has to figure out the spacing of things, and then they've gone ahead and doped it the right way so that you get the 10 volts. No, no, because you'd have to have N-type and P-type doping, and yeah, I don't think most of us have the capability of being able to do that. That's why you go to a clean room, right? You go to a clean room and they have a very specific process because they're, they got to make sure that everything's in contact and right thicknesses and all that stuff. It's actually a marvel at how capable people are able to do this. And then obviously you can use different metals or materials, I should say. You can use silicone, germanium, it just depends on what you're trying to do. Most people, I think, use silicone, but germanium works fine as well. And this is my last slide, SCRs. So essentially, it's a back-to-back BJT. You can see I've got a couple of NP, and I put the gate on one location, and I can get it to conduct in the forward direction, or I can put my gate and run that to the same spot. So essentially, when I'm trying to get conduction in this forward direction, it'll allow it to do. And then when it's in the reverse direction, the other terminal now forward biases the diode, and then you can get direction in both directions. So SCRs, you don't see them all that often anymore. That's kind of older technology, but not exactly. You only have the three. You have the great gate drain source. It's a slightly different. Right, yeah. Okay, any questions? Because our next class we'll be doing, let me stop sharing this. Next class we'll be doing exam review. Then the Thursday we have the exam. And then the Tuesday after that, we'll go over the exam. And then we have one final class for the semester, which will probably be just a main review. But for those of you who are thinking about senior projects, if you haven't picked it out already, it can be hard to do power electronics, but you can do a lot of amazing things with power electronics for not a lot of money. Okay. Anybody in TV land have any questions? I guess not. All right, folks. Have a great day, and I'm going to see you. Have a great weekend. Take care, everyone.